All right, AP students, welcome to your AP walkthrough of an equilibrium expression and constant. I think maybe even reaction quotient, not quite sure. I think I've probably definitely introduced that. But walkthrough video on both a conceptual question in the workbook as well as an AP level. Again, we are going to be doing only parts of AP questions due to the fact that all of Unit 7 is quite integrated with one another. All the subtopics are. So we're not going to be able to answer a full AP question until we've hit later on in the unit. But go ahead and look down in the description box. I will let you know at what time I start addressing the AP level question if you feel pretty good conceptually and you just want to move on. But for everybody else, let's talk about question number 7, page 2 of your workbook. So here I ask you to explain in full sentences how each of the following stresses will affect the equilibrium constant for the following gas reaction. Remember that equilibrium constant is a ratio between the products of a reaction raised to their coefficients and the reactants of a reaction raised to their coefficients. Now, obviously, if you have more than one product or more than one reactant, you multiply. And in addition, you do not include liquids or solids in these. So for the following, what we want to do is we want to consider one immediately knows that this is an exothermic reaction, okay? Exothermic. And we want to explain in full sentences how each of the stresses will affect the KEQ. So what we see is that first we add some CO2. So this is kind of a combo question between Le Chatelier's principle and with specific reference to K equilibrium. So if we add some CO2, what we see is I'm going to put this in blue. If I increase CO2 gas, okay, what should happen? As far as KEQ goes, no change occurs because if I increase my CO2, right, the reaction will shift reverse. So the reaction will shift to reverse direction or to the reactant side. Okay. Now, that's a Le Chatelier's partial way of understanding it, right? Like we know that from Le Chatelier's, but don't mistake Le Chatelier's as equal to KEQ. When we put it in, then KEQ, the ratio, what will happen is the reaction will establish its new point of equilibrium. Well, it will find equilibrium again, which means, and of course, it's reacting and will preserve the stoichiometric relationship revealed in the molar ratio. So, what happens though is when we plug into the KEQ expression, nothing will change because ratios remains constant between product and reactant. Okay, the ratio will remain constant. All right. So in the end, the answer is, let me highlight it, nothing will change, right? KEQ will not be affected. Decrease in the volume of the reaction vessel, okay, at constant temp. Again, nothing will change, okay? Nothing will change as far as KEQ goes, right? Because hopefully you guys are catching on and starting to remember something. Only one thing actually can change KEQ. And that is the following thing. What if I increase the temperature? Okay. So an increase in temperature will, okay, drive the reaction, okay, in the reverse direction because we have an exothermic reaction. So it would be like adding on heat, okay, at the end. And if I increase temp, it'd be like dumping a bunch of product. So it'll drive the reaction backwards to kind of use up some of that excess heat. Okay. So KEQ will decrease. As my product value becomes less and my reactant value becomes greater. All right. So mathematically, we see that the product concentration becomes less and less over time than the reactant concentration. Okay, is what we kind of see. That's my little arrow. Okay, so don't be tricked. Remember, only temperature can actually affect KEQ. Only temp, only factor that affects KEQ. All right. Even adding a catalyst, okay, will not affect, no change, KEQ. Because remember, a catalyst changes the pathway, right? And KEQ doesn't really care about pathway. So, that is kind of your conceptual view. Let's move on now to splicing together and addressing some parts of AP questions. So let's go to page, let me make sure I didn't miss any question. I always want to double check that I didn't miss anything from above. I starred all the ones I wanted to address in a green star. Okay, let's talk about AP question 1, part A on page 7. So you're given that several reactions are carried out, okay, using AgBr, silver 1 bromide, a cream colored silver salt, salt of course meaning ionic compound, for which the value of the solubility product constant KSP is 5.0 times 10 to the negative 13 at room temperature, 25 degrees Celsius or 298 Kelvin. Write the expression for the solubility product constant. So here, remember with solubility product constant, what's unique about it is that because assuming that it creates a solid, right? It starts off as a solid, right? We go from a salt to their dissociated cation and anion, right? A solid salt. Since we never in the KEQ expression ever include the solid, we only then plug into the KEQ expression the product ions goes into KEQ. So what we see is that the KSP for this is the concentration of Ag plus cation raised to its coefficient, which is 1, because it's a 1-to-1 ratio of Ag and Br ion, times the concentration of the bromine ion raised to its coefficient of 1 also. And that is your KSP. So nice and easy, right? Really, really nice. So, hopefully that made sense. And by the way, I believe in about 2 days, I'm going to dig into KSP math. Calculations with KSP coming soon. Okay. KSP is just like a specific expression of K, right? Revolving around specifically ionic compounds. So the next one we're going to go to is page 9, part A, but for long FRQ question number 2. So here, there's a lot of information, okay? Let's not focus on that right now. Let's just look at what the prompt is asking us. The prompt is asking us to write the equilibrium expression for the reaction in terms of partial pressure, hence the little subscript P. We're working with a fully gas reaction, so all we need to care about is the gas. Well, actually, we're not working with fully gas reaction. Sorry, we're working with a solid and gas mixed heterogeneous reaction. But all we need to care about is the partial pressure of the gases, because partial pressure is an indicator of concentration. And remember, we never, ever, ever include solids, right? Solids never included. So just like with the standard setup, we have KEQ with respect to partial pressure is always equal to product raised to their respective stoichiometric ratio over reactants raised to their respective stoichiometric ratios. So according to the reaction, we would get that the KP is equal, KEQ in terms of partial pressure, KP is equal to the partial pressure of CO2 raised to the power of 2 divided by the partial pressure of CO raised to the power of 1. And why did I write CO2? I'm having a brain fart moment. CO. raised to the power of 2 because there's a 2 molar ratio, and CO2 raised to the power of 1. And that's it. Okay. And notice I don't put brackets for this, right? No brackets, because it's not concentration directly. We're not directly talking about concentration. We're talking about concentration through another characteristic that reflects it. Okay. So hopefully you guys are feeling pretty good about this. I think I only have one more starred that I want to go through in another AP question. Let me see if I recall correctly. Wow, I'm really scrolling for a while. Okay, apparently not. So, as you can see, KEQ expressions, okay, are not super complicated. And Q quotient is basically KEQ, but specifically, Q quotient is addressing the instantaneous state of a reaction trying to find equilibrium. So let me just add this quick note that the K is still, sorry, the Q quotient is still products raised to a power over reactants raised to a power. But specifically, this is with respect to a specific instantaneous moment of reversible reaction, whereas K is in with respect to equilibrium. Okay, so when Q equals K, that means the reaction is at equilibrium. Otherwise, we can use Q, the instantaneous mathematical ratio between a moment in reaction of products versus a moment in reaction of reactants, as a general guide of how close we are to getting a reaction to equilibrium. And that is just given the official letter K. So K is technically Q, but Q is not always K. All right. But I wanted to mention that you would still follow the same process, right? If I asked you to write the Q expression, general setup with no values, just putting in the variables of the relevant reagents, you would do the same process. And then what you would probably be asked to do is compare the Q and the K in order to determine whether or not your reaction is at equilibrium or which direction it will move in order to reach equilibrium. So, but I think that will all be addressed in further lectures. So this was a short one. You should feel really comfortable with the overall setup of KEQ expressions, and whether that be partial pressure for gas-based or maybe ionic compound solubility product, which will be its own subtopic. And really, we're going to even introduce acid and base later on. So this is going to be a concept that we carry through, and hopefully this was helpful, if not a nice break on a short one. All right. Bye, guys. Good job. I believe you will have an upcoming AP question lectures will also include a couple short pre-lecture actual note-taking videos. So keep that in mind as you guys plan for the rest of your week. Bye, guys.